My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda, I'd
Mhm.
like to welcome you all to our International Physics webinar. So today it's our 38th Physics webinar. Good evening to all, to those who are watching from Japan, and good afternoon to all here in Bangladesh. Hope you are well and safe from Corona pandemic. So all we know, we are staying in a Corona pandemic situation, and all the institutions have been shut down since 2020 March. So we cannot continue our normal academic program. So we have to start our online program. So we have to adjust ourselves in a new normal situation. And our department of physics, have started some online program. So we have started our online classes and online physics webinar. So I am happy to share with you all that today is our 38th physics webinar, and we have arranged this webinar with the help of your help. So in those physics webinars, the physicists from different countries are coming as a main speaker. They delivered their speech with our students. They shared their knowledge with our students. And by this way, I think students are benefited. So the main aim of our physics webinar is to motivate and encourage our students in this Corona pandemic situation. And we do also believe that this international physics webinar will help them to make interested in physics studies and research. And I am happy to share with you all that. Today is our 38th, and we have successfully completed our 37th physics webinar. Today, I'd like to welcome you all to a joint session between Pabna University of Science and Technology and Cyclotron Radioisotope Center, Tohoku University, Japan, in high energy physics. And we have with us here today Dr. Kazuo Tanaka-san, Assistant Professor, Cyclotron and Radioisotope Center, Tohoku University, connecting us through Japan. And he has already connected with us, so I'd like to welcome our speaker. So good afternoon, Tanaka-san.
Good afternoon. Thank you so much. I'm so honored to this opportunity. Yeah, thank
Yeah,
you.
it's my honor and privilege also to host you in our physics webinar. And I'd like to say thanks on the behalf of the Department of Physics for accepting our invitation. So I'm happy to share with you all that. Today is our 38th physics webinar. And you know that we have arranged a different type of webinar with different field of physics. So today we'll learn in the different topic today in cyclotron and symmetry violation in our world. And for those who are new, I'd like to inform for those that in our webinar will be divided into three parts. First, we'd like to introduce our speaker with all of you. Then our speaker will deliver his piece with our student, for a student. And at the end, there is a session. In that time, anybody can join with us and ask question. So let's go to our speaker ID. So you have already come to know that the title of our today's International Physics webinar, and the title is The Symmetry Violation in Our World. And the speaker is Dr. Kazuo Tanaka, Assistant Professor, Cyclotron and Radioisotope Center, Tohoku University, Japan. And if we see his education and work experience, we can see he has completed his bachelor, master's, and PhD degree from Tokyo University. And then we can see his work experience. He firstly joined as a school teacher, then he joined junior researcher in RIKEN, and now he worked as a assistant professor at the Tohoku University Cyclotron and Radioisotope Center, and at the same time, he is also working as a STEAM sports laboratory as a creative director. So we can see his awards and grant. We can see he have got a lot of grants and awards from different organizations, and we can see his different research. So he is working in symmetry breaking, where he worked how this world exists and what the basic physics is aiming for. And another anti-hydrogen generation and spectroscopy at SUN's ultra-slow anti-hydrogen beam. And another is ultra-fine structure measurement of muonion at J Park in Tokai village. And also precise measurement of electronic EDM using cooled francium at Tohoku University. So we can see his educational and other activities. So this is his group. You can see his work. We feel proud to host him as a physics our physics webinar. So thanks again, Tanaka-san. So it's your time. You can start your session, sir.
Okay, thank you so much. So impressive introduction for me. I'm so honored. So let's start my speech today about the symmetry violation in our world. So can you share my screen? Yeah. Okay, thank you so much. Okay, so I'm very happy that share and exchange idea with people from other country, and I think it's yes, I as you know that this is depend on the due to the COVID-19 problem, which is also happening in Japan, and every university in Japan is also almost close the most critical situation. But now we still under the every class is online now in Japan also. Yes, we restrict in some of the level now. So, but you know what? We also think that this is also the very good opportunity to think about the new idea to how to communicate and exchange the idea with not only from Japan or other country by using the internet or very nice technology. So I am so happy to this challenging stuff. So thank you so much. Okay, so I'd like to introduce myself again. I'm Kazuo Tanaka from Japan, and yes, I'm a member staff of the Cyclotron and Radioisotope Center in Tohoku University. This is a facility belonging in the university, and this is a facility of the accelerator, particle accelerator. So my main work is kind of operations accelerator, or yes, sometimes yes, actually so various type of the researcher visit our facility. So I support for each experiment or project because not everyone is specialized to the accelerators, so that sometimes we buy the not the physics but also the biological researcher who want for example the radioisotope medicine, or sometimes even the company people come to this facility to for example the the main situation is space development. The company which deal with space development who want test their instrument or board or sensor about the radiation damage. The Cyclotron Radioisotope Center is one of the very suitable place to test to radiation damage by using the each particle wing. So I also support such kind of station, and also I am one of the person who curious about the physics, fundamental physics. So I use this accelerator to focusing on my research and physics curiosity. And before I belonging to this Tohoku University, I stay in several accelerator facility such as a CERN, or which is one of the largest accelerator facility. I think Dasan already invites one of the person who involved in the LHC analysis, right? So yes, I think so. Somebody know about the experiment in CERN. And I also, and actually the CERN has a lot of beamline, not only the Higgs discovery experiment, but also a lot of experiment. And I think I can introduce one of the experiment in there today. And also I do my research work in JPAC, which is also in Japan. So yes, actually I love the accelerator and do some fundamental physics by using such a facility. So before the further stuff, I'd like to start very general idea of the fundamental physics and what is the role of the particle physics. Okay, so this is a very general and simple picture about the history of the universe. As you know that this universe is start from the Big Bang, which is happened very long time ago, such as 10, 13 billion years ago. And, you know, the lot of particle is generated from the energy, and it form an atom, molecule, and even the stars, and so many things happen. And finally, our universe, like stars and the Earth and our solar system, is generated, created. So that is our history. So you know what? Every physicist, I believe that every physicist curious that what is going on in any step. Any step means that yes, there are a lot of steps. What is the Big Bang? And how to generate the particle, and why the particle can be formed, the atom, or even the molecule, or the stars. So I think the physicist is one of the person who collaborate each other to separate each section, and I think that the particle physics covers one of this, section, that how to generate the particle and what kind of the physics law or the some force is mediate such kind of the phenomena. So yes, so I'm the one of the person who involved in this puzzle. And actually, there are a lot of puzzle hidden in this section, but I think the most largest puzzle is antimatter stuff. Okay, so I'd like to describe about the antiparticle a little bit. Antiparticle is always generated with particle. I mean, yes, as you know that if we can prepare sufficient energy, we can create the particle. But every time, it's created as a pair, like a particle and antiparticle. And the antiparticle is very similar and symmetrical particle to the particle. And for example, the electron is one of the very basic particle, and the antipair of the electron is so-called the positron. And it's very symmetrical. The mass is equivalent, and the charge is, the quantity is the same, but the opposite charge to the particle. Okay, so if we apply some charge conversion to the particle, this means it's equivalent to change from the particle and antiparticle. Okay, so and another very unique feature is that the particle and antiparticle pair produced from the energy, and also they annihilate to the energy if collide each other. So that is the reason LHC can find the Higgs if we can prepare a sufficient energy which equivalent to the mass of the Higgs, it can be formed. So, the scientists develop a very, very large accelerator to do that. Or if you don't need a Higgs, such a heavy atom particle, maybe you can create a more common particle like pion or muon or proton. Maybe more common size particle accelerator can be created such kind of particle. So the particle physics can do such kind of experiment if we have such kind of particle accelerator. So that is why I love the accelerator to do some experiment. And the biggest puzzle is that why the antiparticle is not existing in our world. This is very, very huge puzzle, I think, because if the particle is not exist, our world cannot be formed like this. So somehow antiparticle is gone, and the particle, only the so huge amount of the particle is remained in our world. So this is the very important history for our universe. So we always think about why the antiparticle is gone. So yes, and there are a lot of assumptions to think about that idea. But anyway, I am a experimental physicist, so I should try to test the assumption or prediction. So yes, I'd like to tell you the history, the scientists, how to focusing on this problem. Okay, the most simple way to think about that idea is create the antiparticle and compare the particle and antiparticle each other. That's I think the most simple way. And if there is any tiny difference in some property, yes, I already mentioned that with the mass is equivalent, but this is just under our observations that yes, it can be changed if we can do some very, very precise spectroscopy. So my first experiment is such kind of a project that we create the anti-hydrogen. Anti-hydrogen means that the hydrogen is a proton and electron. Electron bounded to the proton. This is a hydrogen. So the anti-hydrogen is like an anti-proton and positron. Okay, this boundary system is so-called the anti-hydrogen. Okay, so you know what? Hydrogen is the most simple atom, so that our history does a lot of spectroscopy for the hydrogen. So we have a lot of technology to do that, like laser spectroscopy or microwave spectroscopy, or so many other stuff. So if we can create the anti-hydrogen, we can apply so various type of the spectroscopy which already used to the hydrogen. So our project is create the hydrogen and trapping and prepare the situation to spectroscopy. Okay, so this is one of the experimental area located in the CERN, and this area is focusing on the produced anti-hydrogen. We need the antiproton and the positron. So the CERN provides the antiproton beam, and we can we provided it, and this is the antiproton trapping system using the magnetic field and electric field, so that we can stray the certain amount of the antiproton in there, and also we can create the positron with one of the radioisotope, such as natrium 22, which decays to the positron, so that we prepare some source of the natrium 22 and straight using the magnetic field and electric field and transport it there and make trap in this trap. This is a very interesting idea, but yes, actually I can show you the how to mixing up very shortly. Okay, so wait a minute. So we prepare like for example, okay, for example, we prepare such a potential, electric field potential in there. And you know what? We can trap both the antiproton and the positron in there. If the positron is coming to here, we, shut down this potential wall, and this positron is coming to this area and trapping here. And if the antiproton is coming to here, antiproton is a negative particle, so it can be trapping from this area if we open up this potential very short time. And in that case, we can trade the two plasma in just one place and try to cool down each other. And if the energy of each particle is cooled down in any level, some level, such as the boundary energy level of the hydrogen, then the antihydrogen is created. And antihydrogen is a neutral particle, so that it cannot be trapped by such kind of the electric field or the magnetic field. So it goes through this trap, and we can detect this antihydrogen outside of this trap. That is a very simple general method of what we do in there. Okay, so that is what we do in this trap. It is so-called a cusp trap. And fortunately, I am a so lucky person that I only involved in this project in maybe from 2009 to the 2010, so only 2 years. But in this period, we achieve a first observation of the trapped antihydrogen in this system. And this is a picture we celebrate that situation. Unfortunately, this is during the very long beam time, such as 1 month or 2 months, that we are so, the face of ours is so tired. And even that I am the youngest student in this collaboration, so that I say that I prepare the self timer of the photo, and then I click and go back to this area, but it's not enough time to do that, so my face is not so clear. That is the reason that. So, but you know what? This observation is very huge. So actually, this picture is used for various type of the media or web news or other stuff, so that I'm so pity that I'm not so clear, so that I decided that if I, face such kind of situation in next time, I need to locate it on the just center of the picture, such as her. Okay, anyway. Yeah, she is one of my best friends. Yeah, still, yeah, we collaborate so many projects now. So, okay. Okay, so this is very memorable for me, and I'm very curious about such kind of the project. But still, here's the things. The CERN is the only facility which can provide the antiproton. That means only this area can do such kind of sample experiment about the comparison of the antiparticle and the particle. So, but still there are a lot of particle physicists. So how to focusing on without the antiparticle beam? That is one of the problem for us. But you know what? Physicists can think and consider to solve the problem. And I think there are a lot of clever, scientists. I think so. Some of the scientists, come up with a very clever idea. Okay, I'd like to introduce that stuff. Okay, so we can't prepare the antiparticle. So how to do that? So one of the way is, imagine the virtual world, which is kind of antiparticle world. For example, our world is full of the particle, but we can imagine the world full of the antiparticle. And if there's any difference between the particle and the antiparticle, the phenomena or the world situation of the antiparticle world is maybe something different, right? So if we can do such kind of test or thinking, maybe it works. And what is conversion between the particle and antiparticle? It's very simple. This is just the charge conversion. If we apply the charge conversion from, if this is a positive, this is a negative, and if apply the charge conversion like a minus and plus, this, conversion equivalent to go to the antiparticle world. So let's think about that idea. Okay, so yes, we already do so many experiments about that, but we can think about that. Yes, so now I check the Facebook page, and I'm so happy that so many people, seeing that this, webinar. Okay, like 20 people or something like that. So let's think about that idea. How do you think if we go to the antiparticle world? So for example, I am a god and I can convert a charge if I want. And I suddenly decide that I change and convert every particle charge, like a positive to the negative and negative to the positive. What's going on? And I love this question. And you know what? I ask this question for so many people. And the answer is separated. If I ask this question to the people who is not familiar with the physics, they say, maybe the world is broken or explode or something's changed. But if the people who are familiar with physics, they say that maybe there's no any difference. Yes, so it's very simple. We know that the role of the electric field is very simple. If we prepare the two positive charge, it repulsion. It has a repulsion force like this, but if the charge is different as positive to negative, it attracted. So if we change this word to the minus, plus, and plus and minus, the phenomena is exactly the same. Minus and minus, and also the go away, and plus and minus is go to the minus and plus. It's also attracted. So it seems that there is no any difference each other. But yes, we already know that our world breaks the charge symmetry. Okay, I'd like to show you the very, very basic and popular example about that. Okay, this is an example about the pion decay. Pion is one of the particles which has a very short decay time, so that its decay very, very short time to the muon. And you know what? Muon, if the positive pion decay to the muon, every time muon has a positive charge. And yes, let's think about the spin, the polarization of the muon. I mean, the possibility of the spin. And maybe there are two candidates. It's along the spin direction is along with the momentum of the muon, or antiparallel, right? Okay, so and you can test what's going on with the beamline. I mean, every muon beamline use this technique that every time A is happen, we can't see the V. We already know that. So it's very interesting. And okay, so what happen if we convert the charge? Yeah, there are two candidates. The pion is go to the pi minus, and muon convert to the mu minus. And the spin direction is also has the possibility of the clockwise and anti-clockwise, or the relationship between the momentum of the particle and is parallel or anti-parallel. Okay. So the interesting is that we should believe that yes, this is assumption. We should believe that the relationship is exactly the same as like this. A is converted to the B, C if charge conversion, and B is converted to the D if we apply the charge conversion, so that the percentage of the ratio of the what happened is like should be like this if we believe the charge symmetry. But we already know its opposite. And it implies that the charge symmetry is violated in our world. So that is happen in our world. So I can say that yes, charge symmetry is violated if we think about the weak interaction so much. And this idea is very, very fascinated. And so many physics scientists start to think about the fundamental symmetry. Yes, this is one of the fundamental symmetry, that's the charge symmetry. But how about the other stuff? For example, yes, it's totally violated relationship. But if we apply the CP symmetry, it means that we convert the charge and parity at the same time. I mean, A go to the D, B to go to the C. It seems okay. 100% is 100% and 0% is 0%. So we still can't believe that CP symmetry is okay. And now we going to the test of the CP symmetry, and so many projects is happen in about the CP symmetry in so many system. Yeah, actually there are a lot of particle symmetries. So okay. Oh my god, so many comments is in the Facebook. Okay, can I check the little bit? Okay. Wait a minute.
I think we can discuss question later. Maybe it's okay.
Okay. Okay. So yes, maybe yes. Maybe most of the comments about the stuff which I mention in more later parts. So
Yeah. Okay.
okay. Okay. Anyway, I see. Okay, so let's. Sorry. So I'd like to go step to the next slide. Okay. So I already mentioned about the parity symmetry. So the physicist curiosity is go to the next step. I mean the CP symmetry. And what is that okay or not? But I also mentioned about what is the parity symmetry, the definition. Okay. Yes, there is a more strict definition, but today this is a very general lecture, so that this is just approximated. But I'd like to introduce a very simple idea. Yes. About the parity symmetry, it converts every direction. I mean, the left and right, and forward and backward, and upward and downward. But let's think about only one direction. I mean, just change from the left to the right as a mirror world. As you know that, yes, and the mirror world has a more complex definition, but yes, just think very, very simple. In the mirror world, every parity is convert like left is right and right is left. And think about the parity symmetry is the idea that what's going on if we go to the mirror world. And this is, and we also change this idea to the asthma problem, which is also a very popular idea that, yes, this idea is exactly the same that think about, can we introduce the definition of left and right to the alien? Okay, the alien means that people who do not have any common idea or, culture. For example, if I met with a Japanese person, there are a lot of stuff to tell the left and right in Japanese culture. And also, I think in your country, there are a lot of stuff about that. But, alien don't have that. So if I want to tell about that kind of idea, I need to only use the physics law, which believe to apply it in any area in the world. So I think it's a very difficult question, but yes, anyway, it's the same idea. And yes, actually, scientists focusing on this problem so many times. But anyway, I want to go more deeper stuff about the parity symmetry. So before that, I prepare a quiz today about the more macro about the parity in our world. Okay, and I know that there is a Facebook comment, so please make your answer with the comment. Okay, so the rule is that I like to show the pair of photos. And I take this photo several years ago. And actually, yes, this is a photo of one of my dinner dishes. And the one with the picture shows the real dishes, and another one is flipped. I mean, left is right and left is left, reflected. So let's think about which is the real picture. Okay, so let's do that. And I think it's very important quiz to think about the parity symmetry. Okay, anyway, this is a picture. Okay, so I gave you a short time to think the idea. So please feedback me to the answer and also the reason to why you think what is real and not. Okay. And you can ask me if you want to know about the cultural stuff. Okay, so I think it's a little bit difficult question for your country, but okay. Anyway, I'd like to introduce that what is going on when I show this picture for the person, for Japanese or even other country people. Okay, as you know that this is a Japanese traditional dishes. So for the Japanese person, we have a lot of knowledge about the regulation to how to position the dish or even the position of the chopsticks. But okay, so so I mean for the Japanese person, this picture is so complicated. The reason is that usually we put the chopstick as A, but we put the rice and soup like B. So the rules mixing up each other. So I mean, not so many Japanese person can't answer this problem. But yes, if you can ask me that which which hand you use to eat, this is a very good question, I think. And I am the very rare person that I am left-handed to eat something. And this is very rare in Japan. I mean, maybe the 93% use the right hand to eat something. So, not the Japanese person asked me to do that because this is not common. So, that is what happened when I show the people this picture and to make some discussion about that. But here's one thing. You can find the fish in there. And this is a very popular fish in our country. And this is so-called flatfish. And I don't know you can try in your country or not, but yes, you can easily try in Japan. And this fish is very unique that this fish breaks the parity symmetry. The position of the mouse is, yes, we believe that the position of the mouse should located on exactly the center of their face, but somehow the mouth of this flatfish is located on the right place on their face. So, the people who love cook can answer by using this idea. And if I ask the people like 10 or 20, maybe 1 or 2 person answer from this idea. So that is why I think this is very interesting stuff. Okay, so I want the things I want to say from this picture is that there are a lot of parity symmetry exists in our world, but usually if I ask the student what kind of parity symmetries happen in our world, most person answers that very artificial stuff like typography or user interface, like yes, chopsticks is one of the example, I think, or even every character of our world is break asymmetry. And yes, and I think this is everything. This stuff is embedded from us. People, human invent the typography or user interface by ourselves. So, and I think we can, separate the each asymmetry like this. And yes, for example, yes, some of the our body or our creature also break the symmetry. As you know that our body, yes, it seems very symmetrical, but inside the body, there are a lot of asymmetry. Most of the tissues in our body break the symmetry, right? So yes, but nobody knows. Everything is unknown. The reason that but yes, someone, yes, this is not the scientific evidence, but someone believes that there is a kind of relationship between the why we make a symmetry typography or other stuff like left-handed or right-handed from our body. Then also we already know that we already know that more in macro fields that molecule also break the symmetry. For example, that amino acid is one of the very, very important molecule for our creature, have a chirality, so that one of the pair of the chirality is only used to our creature, and I think it's very, very weird stuff. But yes, somehow the thing is do so. And we believe that the physics law, everything is under the physics law, and physics law, control the phenomena of the particle, and parity violation is also happen even in the particle physics we already know. And the right figure also show that one of the example about that. I mean, cobalt 60 is very famous experiment history that this is maybe the first observation of the parity symmetry. It happened in maybe 60 or years ago, or yes. So yes, that's happened in our history. So you know what? Yes, the parity symmetry is broken, and charge symmetry is also broken. This is very clear. We have evidence, and we can, test this stuff only from this idea that, charge symmetry is a relationship in the A to the C and B to the D, and a parity symmetry relationship is A to the B and C to the D. So this relationship is already broken. But yes, we hope that CP symmetry. But you know what? We already know that CP symmetry is also broken, which, yes, there are several evidence about the B boson or other kaon or other particle experiment is already held. So, and I'd like to introduce this stuff, but today I want to tell third type of the fundamental symmetry, which I focusing on this facility. This is the time reversal symmetry. And we already know that the time symmetry, time reversal is exactly the equivalent to the CP conversion. So that if I say that I want to test the time reversal symmetry, it means that to test the CP symmetry, if we believe that CPT symmetry, yes, there are a lot of story in there. And some of the comment mention about that kind of idea. But anyway, okay, I believe that the time symmetry can be important role to describe about the particle and antiparticle puzzle. Okay, so yes, and maybe you can come up the idea how to test the time reversal stuff. And I think the most popular target is EDM of the particle, which is maybe the very, very popular target to test the time reversal. Okay, I show you about this one. Okay, this is very weird story. Yes, but okay, so the EDM, the definition of the EDM is okay. The precise definition is electric dipole moment of the electron. But if it's not so clear, I'd like to say it's kind of charge distribution of the electron. It's very weird idea because electron is a sizeless. But you know what? Even the electron is a sizeless, but it has a spin. Also, it can have some electric dipole moment. And I want to mention that kind of idea to more simplify. Yes, it's kind of, charge distribution stuff. Okay. So, and also I'd like to adding the one more definition that this EDM is along the speed direction. So if the spin is upward, the EDM also upward. Okay, this is the definition of the EDM. And if the EDM is exist, it automatically implies the violation of the time symmetry. The reason is that, okay, if we think about the time reversal, it should be like this. The spin should be opposite if we think the time reversal, right? If go like this, if the time reversal, it should be like this. So yeah, spin should be changed, but the charge distribution or the electric dipole moment cannot be changed by the time reversal due to this is kind of very static electric stuff. So okay, but I already mentioned that there is a definition that EDM is along the spin direction. So in that case, it should be like this. Charge also, the direction of the EDM is also changed by the change of the spin direction. So if EDM exists, it implies the time symmetry violation. Okay, so how to test this idea? And the test method is also very simple. Okay, let's prepare the electron and polarize to upward and apply the both magnetic field and electric field at the same time and compare each other of the energy level between the relationship of the magnetic field and electric field is parallel and antiparallel. And if the magnetic moment is also flipped by this magnetic field, so that but you know what? If the electric dipole moment is also exist, it also flipped by the spin, but the electric field is not changed, so that the energy level of this parallel relationship and antiparallel relationship, there is a difference of the multiply the EDM factor and electric field. So if we can have any difference between the energy level of each system, it implies a EDM. That is what we do. And as you know that this is very weird idea that EDM exists. Not so many people believe that. But and also that standard model rejects this idea. If we believe that current standard model, the EDM is so tiny. Yes, it can be exist. It can be exist, but it almost sorry. The differential is almost 10 to the minus 40 electric per centimeter. That is what the standard model predict. And current upper limit of the latest experiment is like 10 to the minus 28 electric centimeter. So it's very, very far. So that we believe that if the standard model is right, we can't observe the EDM forever. But yes, we believe standard model can be changed from other possibility. Maybe some of the comment mentioned that the SUSY, the supersymmetry particle, or yes, everything's okay. Axion, or I don't know, the dark matter. Yes, it's very related to each other, but anyway. Yes, so yes, there are a lot of assumptions based on such kind of the new particle or new interaction, which can be implies EDM. So yes, we should test to we can test such kind of new particle or new theory with EDM. If we can observe the EDM, it implies a new physics, or if we can achieve a more lower upper limit of the EDM, it can be reject the new theory which is created by the theorist. So it's closely related to such kind of theoretical prediction stuff. So okay, this is what we do in this facility. But this is very, very tough experiment because you know what? 10 to the minus 28. What happened? Okay, so the precision is ultimately difficult for us. And we do everything to improve. And what we do, what the unique stuff in this facility is using the francium atom. Okay, francium atom is the largest, heaviest alkali atom. And you know what? The outermost electron is only one, so we can use this electron to test the EDM. And yes, this is very suitable. Alkali metal is very, very useful because in general, we can apply the laser trapping and cooling technique, especially the alkali atom. So, we can cool the francium even millikelvin or even the microkelvin. It means that we can achieve very precise experiment. And also that this is a very huge atom, so that it has a very large electric inner the nuclear of the francium, so that it multiply and enhance the EDM like almost 900, so that it also contribute to improve the precise of this experiment. But however, the problem is the francium is not stable. This is a radioisotope, so it has a lifetime like 3 minutes. So we need to produce the francium every time, which we do. So that is why I use the cyclotron accelerator in Tohoku University to produce the francium every time we want the spectroscopy. Okay, so and this is one of the picture of a facility. And okay, this is a beamline of the francium. Maybe you can see. Yes, today I'd like to have an online tour of this facility after my talk, and maybe you can see one of the part of this facility. Unfortunately, we remove the rest of the beamline now. So, but you can see this very large, bending magnet in there, and this beamline provides the oxygen beam, and we place a gold target on there, and the fission reaction is happen between the oxygen and gold, so that the francium is produced. That is what we do in this beamline, and transport this francium beam in this trapping system, and using the laser trapping technique to cool down the francium, what we do in this facility. And also I do this technique in Riken, which is also the one of the facility which uses a cyclone accelerator. So that we do, and I think it's very unique. Okay, so that is my story. But okay, I'd like to talk one more stuff later.
Great.
Okay, sorry, and then let's go to the discussion session and or the online tutorial session. So okay, so anyway, that is my history, and okay, so I'm very curious about such kind of fundamental symmetry experiment, and I love that. And also, I'm curious about how to, share the what is the interesting stuff in our physics. And it's a little bit difficult in Japan. I mean, recently in Japan, the fundamental science is not so strong. I mean, recently the government just focusing on more investigative stuff like technology stuff or AI or so yes, not so many people curious about the fundamental physics. So I also involved in some education activity to enhance this stuff. For example, I invite several secondary school students to try this Francine production. Maybe once or twice per year, I do some such a experimental week to invite the student to do that. Or I also make a collaboration of that kind of the enhancement of the research work for the secondary school student, especially the cosmic ray. Yes, we are also the specialist of the development of the detectors, so that yes, I developed a very cheap cosmic ray detector like this. This is very cheap and very useful. Just connected the USB to do that, and I distribute this detector to so many schools. Okay, so this is just on the candidate list of the which I give this detector, and now over the 20 and now even the 30 schools receive this detector and start their activities. And I also support their activity. I mean, yes, I hire the undergraduate students, maybe 4 or 5 undergraduate students to focusing on such kind of support stuff. And actually, yeah, there are a lot of research stuff is created in Japan. So, I mean, what I want to say is that my work is a fundamental physics, and I also am curious about a lot of stuff, and especially the education. So I involve a lot of projects about the education, like particle physics, like the how to use detectors. Yes, and I think it's very good opportunity for them. And also, yes, sometimes I have a project about more general education stuff like programming or other stuff. And I think it's very important that such kind of physics scientists involved in such kind of field and education. And yes, so now, and I find a lot of fields that we can connect each other. I mean, sometimes I am the one of the director of the company which deal with sports education and sports research. And I think it's very interesting that in sports field, there are a lot of analysis going on, and some of them, the scientists of the physics scientists can contribute to this analysis. It's very similar. So I'm recently I found that there are a lot of new field in in each field, so that I'm so happy that I can find a new field and new idea. And the most important thing is to broaden the boundary. And I think this opportunity is very valuable for me. That I think maybe this is the first time to discuss and share the idea with the Bangladesh people, so that I'm so fascinated in that. So anyway, okay, that is my history. Okay, so thank you so much.
So thank you, Tanaka-san, for your nice presentation. So we have got some question in the Facebook comment, and also we have a guest from Japan. So if you allow, so I can add him, and we can read the question. So we have already connected with us.
Konnichiwa. Hey.
Wow, nice guest. Oh my God. Hi.
Welcome, Rufik Bhai, to our.
Thank you very much.
Thank you so much. I mean, you invite this opportunity, so I'm so yes, appreciate to you that it's so happy.
Okay, since I am so happy also to you. I enjoyed your lecture from the beginning, and I tried to understand, but unfortunately I am not involved to the particle physics, as you know. So but as a physics student from my bachelor and masters, I have little bit idea. So really I enjoyed when we were the student in the university, we read particle physics and quantum physics, but at that time we just read for the examination and others. Now the time is for understanding. So I really enjoyed, and hopefully the student, those are interested for the high energy physics, it very fundamental and very beginning topics of this high energy related physics. Today's discussion by the Professor Tanaka. I am also happy to see you. Finally, I am the thanks that you agreed for this lecture to our student. So let's. I just no question. So only the discussion about that one. I can say one things about that you are involved in the sun, and you told that the anti-hydrogen experiment is is done in that place. So only anti-hydrogen or others element they are doing that one. Please say something about for our student.
Okay. Yes, actually, it's very interesting that anti-proton beam lines only exist in the CERN, but it distributes the full area in each time period. So actually, there are several projects in there, and I am one of the person in one of the projects. But most of the project is just focusing on to form the anti-hydrogen in this period. But now most of the projects succeeded to do that. So they go step to the next step now. So, but yeah, still anti-hydrogen. But there are several unique experiments going on there. For example, we already done the spectroscopy of the anti-hydrogen in very precise region, and still we confirm that there is no any difference property between the hydrogen and anti-hydrogen, such as the precision of the ppm, I mean the 10 to the minus 6 level. So yes, but still we can improve this value, so we hope to do that. And also one of the very unique experiments is going on is that they test the gravitational stuff. I mean, there's no any experiment about the gravitational force between the particle and antiparticle. But we can do that if we can cool down the antihydrogen very, 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 very low temperature, like I don't know, micro Kelvin or nano Kelvin. In that case, the gravitational force can be observable, so that it's drop. and one of the projects to do that. Okay, that is the current situation. But yes, we hope that we can do more, create a more heavy antiparticle
Yeah,
subjects.
maybe other element. Okay, thank you. So I would like to know from you only other things because the high application of high energy application to the universe is really many challenges. So what is the real application in near future of the say parity violation or antiparticles? So real application of the antiparticle in the universe. I'm just curious. Yes, maybe other student also.
Okay. Yes, this is very difficult question, but yes, we believe that some days there, some of the idea can be applied in some yes field. But actually, yes. I mean, there are several examples in our history, physics history. But I think that the current position of the high energy physics is so far from our, common lifestyle, so that I can't imagine that. But yes, we should think about that idea. I think the very basic and simple idea is that the very technology stuff. I mean, if we develop the detector, we need to develop the original sensor or semiconductor, even that. So, but it's very, sometimes it applied to the common sensor sometimes. So such kind of the technology sharing can be, it can be imagined that. So
Yeah, yeah. Okay. So, and it's not a question. It's I told you that you also told you have the cosmic ray detectors. So I'm happy to say to our student of Bangladesh, those are student of graduate and undergraduate level. Hope so we can get one detectors from our guest.
yes, yes, I hope so. I mean,
I will be very happy. To one.
I'm sure that.
Yes,
And,
yes, okay.
I mean, you know what? Yes, we already distributed the very dominant area now, but now we change. I mean, we should broaden the boundary so that, yes, next week I deliver one of the detector to Argentina.
Great.
Hope so.
I
Hope so.
have
We
one
can-
of the educational collaborator in Argentina.
Bangladesh.
And-
Okay.
Hopefully, we will also get in your future.
Yes,
And
because
thanks, Rafik Bhai, for
I mean-
introducing these things to us.
And
okay, let's go for discussion. Yeah, for the
So,
question, any
Yeah,
question, right?
thanks,
So,
Rafik Bhai, because without your help, this webinar actually will not happen. So, all credit goes to you. So,
no, it's
okay,
my pleasure that we are because you are doing a lot of rules for our students. So it is my very small contribution to your webinar. I believe that one, but
thanks,
I'm
Bhai,
very
again.
happy to be part of
Yeah,
you.
we also feel proud that you also help us. So let's go to our discussion and we can read the question. We have some question. So first question. So sir, is there any new kind of universal symmetry along with CPT?
Okay, so yes, CPT symmetry test is a very complex one, but actually, I already mentioned about the antihydrogen experiment and antihydrogen experiment. Do a spectroscopy and we can get the property of the antihydrogen, like charge or magnetic moment, and compare each other. And this is the directly meaning that tests the CPT symmetry. If there's any difference between the mass of the particle and the antiparticle, it directly meaning that violation of the CPT symmetry. And I mean, it's very difficult to describe very short, but there are a lot of such kind of stuff. I mean, test the CPT symmetry. And you can find the particle data group list that they summarize every CPT symmetry test and every upper limit. But you know what? Still, we don't have any idea or suggestion that CPT symmetry is violated, and I don't believe that. So anyway,
Okay, so thank you. So we can go to the next question. So from nothing, Big Bang, it appears particle and antiparticle. What produced this separation? What produced Big Bang?
Okay, that is what we curious about that. You know what? The every phenomena, we believe that every phenomena is based on the physics law, and physics law is based on our experimental evidence. And we already know how to create the particle and the antiparticle from the nothing by using the particle collider. So we just believe that everything is that the phenomena is exactly the same is happen when we do the with the accelerator collider, so that okay, that is yes, it's very difficult to answer, but yes, we believe that because we observe the particle creation from the particle collider.
So thank you. We have another question. We can. So
Wow.
since there is a associative conservation law with symmetry, if there is a violation of symmetry in early universe, in the case of antiparticle, there should be a violation of conservation law. How can something be created if there is no associative quantity to nullify or conserve that?
Okay. Yes. So it's. Yes. Yes. It can be happen. I mean, we should care about the difference between our current situation and the beginning of the universe. I mean, there's a lot of stuff is changed, so that yes, but still, we still believe that there is a ultimate universal law is exist. And that means this law has some conservation stuff, and it is ultimately fixed in this law. But our law is limited, so that it can be changed. So what we do with this sequence is how to improve our law to more ultimate one, so that the final goal is that we can neglect the such kind of break of the conservation law in any field. So yes, but your mention is, I think, right. So we should think about that idea. Yeah.
Yeah, thank you. So, is there any direct experiment confirmation of the existence of quark?
Existence of the quark. Okay. 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 I do not have. I'm not sure that this is the answer, but let's study about the proton and the proton collision. I mean, the proton-proton scattering is a very interesting example. That if the proton is sizeless or there's no structure, we can analyze the data that check whether the proton has no structure or not. And this experiment shows that there is a kind of structure, and it has confirmed some quark stuff. So please check such kind of scattering experiment.
Thank you, sir. So we have another question. So, what do you think about the minimal supersymmetry? Maybe you have already,
Okay, so
and maybe similar. So, what do you think about strong superposition? So,
okay,
maybe you already talked about.
okay, you're a student, so curious about that symmetry somehow. Okay,
This topic is very interesting for them. So,
okay, okay. So it's very very delicate question that, but I am the experimental physicist, and I try to test all of the stuff, and supersymmetry theory is very very difficult because so many experimental evidence can be restrict the boundary of, I mean, the energy level or so many other boundary a lot. So even the minimal supersymmetry, the possibility of this theory is so tiny due to the lot of experiments now. So I feel that yes, the possibility is not so high, but still the theory is so clever that they can improve easily. So I don't care. I don't care. We don't need to fix the current evidence. Just improve the theory to fit the experimental evidence. That's what they do. So I hope that kind of the things is going on in the future. Is that the answer?
thank you. So, I think we can conclude as we don't have any question.
Okay.
So, we can visit the lab if
Okay.
one of your students are waiting with us.
Huai-san, could you turn on your video? Okay.
Great.
Okay. So I'd like to introduce the facility. Okay, this is the cyclotron accelerator in our facility, and you can find the blue and red structure in there. And okay, that is one of the largest cyclotron accelerator in the university. And okay, question, can you more closer to the? Okay, thank you. And the cyclotron accelerator is accelerate the particle by the oscillated field. It applies the oscillator field, the electric disk, and the particle accelerator in the gap of this disk. That is a very simple explanation. And also, this particle is rotated and the cyclotron accelerator. So, and this rotating is due to the very strong magnetic field, which is applied. Can you see the magnetic winding stuff? Maybe brown, very thick structure. Yes, that's one. So it apply almost a 1.7 Tesla magnetic field. I don't know it's common with you, but it's very, very high magnetic field, such as if you try a MRI inspection, it's almost a similar one. Okay, and the Hwa-san, can you far from okay, and you can see the red cylinder structure in the left side, and this is the RF cavity, which amplifies the electric field and apply to the disk. And it's the electric field is like over the 10,000 watt, and the frequency is like 20 megahertz. It's so high, so it's, and usually we control these parameters to optimize each particle. I mean, the cyclotron accelerator, so various types of particle, such as the proton, or even the oxygen, which we use in the Flassman experiment. And So that is what we do using this accelerator. And actually, yesterday we have an experiment with company. I mean the space development company who want to test their module. And now we cool down this accelerator
Yes,
now.
yes. I am also enjoying because I many times visited inside the SIDIC. So
Oh my
now
god.
I am, yes, yes. I think Bangladeshi student is very lucky. Not only Bangladeshi student, many others can see these facilities is really difficult to access in this SIDIC laboratory. So I
Yeah, we
think
agree.
so this
Also,
video you cannot get more idea, but you can think about how big this type of facilities at least.
Okay.
Okay, Sensei, continue.
Huai-san, can you go to the target room? Maybe yes, it's take a little bit time to do that. So
Sensei, I have the experiment next week, you know that, for a proton beam. I irradiate water phantom.
okay. Oh, okay. Yes, maybe yeah. The schedule is almost fixed, right? So
Yes, next week, 16th of September.
next week. Wow.
Yeah. Yeah, I'm very excited to see my image of proton beam using the O15 and the nitrogen 13 radioisotope is like that, the positron emission.
Yeah. I know. Very nice. Exciting.
Yes, so
Okay. So
it's
could you? Where? Sorry, I missed your mention about the schedule. Where is your? Uh,
16th of September.
okay.
16th.
It's interesting
Yes,
because you know what? The Rico who shows the cam in
yeah,
and
yeah, yeah.
she, her experiment is will have in 15th to the morning of the
Oh,
16th.
so,
So maybe it's just before your experiment. So
yeah, okay. So I have a plan to take a video. I talked with Otabe Sensei. He told that he will arrange because it is our first experiment of this type of
yeah.
experiment. You know that I have present my instrument of PAM
Mm-hmm. Yeah. Yeah.
simulated also. The good
Yeah.
news is I also simulated using Giant 4 gate code
Okay.
last
Okay.
week, and we found the same result as the fits.
Oh wow, that's nice. I think
So
yeah, it's a this
Hiroshi
comparison.
is very excited, Otabe Sensei. Yes.
I see. Yeah, it's exactly the same thing is happening in our laboratory. That in our laboratory, that fit is very common simulation.
Yeah,
But
yeah.
not so many people use the GANT before. But I use the GANT usually so that yes, the things
Yes,
happen.
we started Jan 4 and Otabe Sensei. I am the first student. I start the Jan 4.
Ah, really?
Yeah, yeah.
Yeah, it depends on the field, right? I mean, maybe the high energy field like serum or other facility use giant flow very commonly, but yes,
Yeah, yes, yes.
fits
yeah,
is
J-Park also use Gen 4.
Yes,
yeah.
but FITS is the efficiency of FITS code is very high other than code
Mm.
because it is very database related, and so I'm very happy to work with both codes.
Okay, maybe she has
Ah,
connected
okay.
again. We can.
Yes, now
Okay.
she goes to the target
Uh,
room. I mean, it's take a certain time to reach this target room, so
Oh
yeah,
yeah, yeah.
and
thanks her.
now, okay, so this experimental area is focusing on the two projects. The one is about the Francine experiment, which had in the west side, and maybe you can see this bending magnet, and the rest of the beam lines already removed now, so maybe you can't find anything about. So, but the RICO use the right part of the um, area, and this is focusing on the proton therapy experiment. And I think that she can try to introduce her work a little bit. So, Rico, can you explain what You
Hi.
want to do that?
Hi. Hi
Hello.
everyone. I'm Riko Hashi. I'm at the 50-second beam course. The cyclotron accelerator is beyond this room. The beam accelerated by cyclotron is delivered by this pipe and magnet. で、ビームが The film is 12 meters, and we set the target on this stand. Now I'm setting water tank, water. So
Water phantom. Yeah.
I'm studying proton therapy in this beam line.
Same field of sensei. My.
Yes.
Proton therapy plays an important role in cancer treatment because the proton particles have superior dose distribution called black peak, easing physical and mental burden on patients. Monoenergetic black peaks of protons occur at the end of the range is in a narrow depth dimension of only several millimeters in tissue. In order to irradiate cancer lesions of larger dimensions with black peak radiation, the peak region can be extended by spreading the energies of the incoming particles. Now, I'm developing this plate called rich filter by using 3D printer. So,
Yes, I have seen.
Yeah.
it
Yeah.
look like pyramid. So
Very, very interesting. Yes, very really interesting.
rich filter can modulate beam energy and black peak region. So we can generate by using rich filter. So generate split at black peak fitting the cancer lesions of patients. So I will try to evaluate this rich filter in next week. So we have experiment. So
Okay.
I hope to get a good
Best
data.
wishes for your experiment.
Yes.
Yeah. He's so
So,
focusing on the next stream time also.
yeah. So,
Thank you for helping us.
can I know from you which energy level or energy range are you using for the proton beam from minimum and maximum?
Okay, so
Can,
Hwai-san, what is the energy of the proton beam in your course?
80 mega electron volt.
Maximum is 80 mega electron volt.
80, yes, and minimum is the maybe 50.
Yes, depends on the situation, but yeah. So
Okay.
I think it's very interesting that this area has a two beam course, and one of the course tests T symmetry. I mean, the very, very fundamental physics, and it's very close by the proton therapy experiment course. And I involve these two experiments at the same time. And I mean, yes, several times I use the left course, and next week I do experiment in the right course. And I think the idea or the technology using these two beam course is very, very similar. So I think maybe this is one of the answers that to the request at the this is the one of the solution to how to share the idea, very applied stuff and the fundamental stuff. That yes, I mean I bring a lot of technology to this beam course, proton therapy course actually. So yes, it's not so very new technology, but even it's very common. There are a lot of new stuff and the new idea each other. So that yes, I'm so excited to do that in this course. So yes, that is what I do. Yeah.
So thank you. Thanks,
Yeah.
Rico-san, and thanks Rafik Bhai, and thank Tanaka-san for your wonderful session. So from the beginning, those who are connected with us, I think all have learned a lot of things. And this lecture is very helpful for those who are studying in nuclear physics and particle physics. So I'd like to say thanks on the behalf of the Department of Physics, Pablo University of Science and Technology. It's a great opportunity for our students and those who are watching this webinar. And I'd like to say thanks for all those who helping us in arranging this webinar. So thanks again, Tanaka-san and Rico-san and Rafik Bhai for this session.
Thank
thank
you
you.
so much.
And hopefully
Thank you.
Thank
see you
you.
again for
Thank you.
another webinar.
Thank you,
Yeah.
Sensei. Arigatou gozaimashita.
I hope see you again. Yeah. Thank you so
Thank you.
much.
Yeah, sure,
Bye.
Sensei. Sure, we can join very frequently. No problem. Okay.
Yeah.
Bye for
Thank you
today.
very much. Thank you,
Thank
everyone.
you.